to kindly take the chair and preside over this technical session. Along with our session chair, I request our session co-chair, Dr. A.P. Singh, Honorable Secretary IGS, to kindly join on the dais. Thank you, sir. With your kind permission, we shall now proceed with the technical presentations of this session. So I hand over to you, sir. Thank you.
Yeah, very good afternoon, all. So it's a proud privilege for me to welcome Professor Deepankar Choudhury to deliver the prestigious 47th IGS annual lecture. Before that, there will be a small introduction by A.P. Singh, because Deepankar was specific that if we go on introducing him, there is so much to introduce. So it will be there in the slides. But then a few words from the secretary before we hand it over to Deepankar, because he wants to make use of the full time.
I think there is no need to introduce Professor Deepankar Choudhury. He is a well-known personality in our fraternity. So with these two sentences, I welcome Professor Deepankar Choudhury to take us.
Namaskar. Good afternoon, everyone. First of all, my prayers to God Almighty and my teacher present over here, and several of my students and well-wishers. Thanks to all of you. Thanks to IGS for giving me this opportunity. I feel really honored and humbled in presence of all of you presenting this 47th IGS annual lecture. When I tried to select the topic, I was thinking on which I should speak, as this journey is about 25 years. I still recall my first paper I presented in IGC-2000, which happened at IIT Bombay way back. So this is exactly, I'm completing 25 years attending IGC, also as well as my paper publication and research journey. So a quick overall acknowledgement. I would like to first of all thank all my teachers, mentors, guru. I'm really fortunate that today one of my former teachers, Professor T.G. Sitaram, is present over here. I think this is one of the best opportunity a student can have, that he's presenting in front of the teacher. So my all teachers of ISC Bangalore. Also, I'm very fortunate. I have another teacher from my undergraduate college of Jadavpur University, Professor S.P. Mukherjee, present over here. So thanks to all my teachers for grooming me in my earlier days. Thanks to Indian Geotechnical Society for honoring me with this prestigious 47th annual lecture. And also a special mention for IGS Surat chapter, IGS Goa chapter, and IGS Vadodara chapter, because they are the one who were behind me that, okay, let us nominate you for this annual lecture. And thanks to these chapters for believing in me. And also NIT Jalandhar for such wonderful arrangement, and mainly Professor Agnihatri and his able team for all the arrangements and everything for IGC 2025. All my collaborators from India and abroad, several of you are present over here. I'm standing in front of you because of you people only, for all your support. All my former and present research scholars, several of PhD students, actually 24 of PhD students are present over here from my lab out of 30. Really thankful to all of them for coming over here. Several of postdoctoral students, I say postdoctoral fellows or scholars, 4 of them are present over here out of 6, and several of MTech scholars. Several funding agencies for various projects which we were involved, and associated organizations. Of course, my workplace, I started my academic journey as a faculty at IIT Kanpur, thanks to all my colleagues of IIT Kanpur in those days, and the present day IIT Bombay. Since last 23 years, I'm serving there. Also, my regards to my parents, thanks to my family. I'm thankful to my wife, Nilanjana, she is present over here, and my all friends and all well-wishers, and Almighty God, my pranam. We all have heard today morning, our chief guest, Professor Sitaram, has mentioned that in Viksit Bharat, India's main focus, one of the main focus is actually infrastructure growth. So when we go for infrastructure growth, you know, whether it is bridges, buildings, power plants, oil refineries, dams, energy sectors, transport sectors, tunnels, etc. So we need to have a strong foundation. If there is any failure of this infrastructure, that severely hampered the economic growth of nation. So we face several challenges how to make disaster resilient infrastructure for geostructures. So I will be talking or focusing only on earthquake majorly, also a little bit of tsunami and landslide prone regions, how we make the geostructures of foundation stable. And this is a summary of, as I mentioned, last 25 years of our Geotechnical Earthquake Engineering Lab research group, how we started with a basic research and then through several real-time field projects, how we converted to translational research. So thanks to all who are involved in this journey. And this journey, of course, there are several other stalwarts who are working on this area, but today, due to the time limitation and this annual lecture, I am only focusing from our lab last 25 years we have done. We have stalwarts present in geotechnical earthquake engineering. I know Professor Kayan is present over here from UC Berkeley. Professor Gopal Madhavushi is another person who is present over here. So, Professor Sitaram himself is a towering personality on this topic. So my regards to all these people, those who have worked on this area earlier. When it comes to the first selection of any infrastructure, the first important thing we look at the site selection and the geotechnical investigation. For that, we have to first identify, which many cases we don't do, that whether the site comes under low risk region, moderate risk, or high risk region. Depending on the risk, remember the risk is not same as hazard. It's the combination of hazard, exposure, and the vulnerability, and accordingly, depending on the risk at the site, we need to go for whether detailed geotechnical investigation or normal geotechnical investigation. If detailed geotechnical investigation, what are the high quality testing we need to do at site as well as at laboratory, and from that site specific condition study and analysis, how we come with the solution. As also in the morning, our chief guest mentioned that it is a case specific, location specific. Also, our IGS president has mentioned about this, that each problem of geotechnical engineering is specific and non-identical, like structures and other things. So when it comes to specifically the selection of dynamic parameters, then things become little more complicated, because why the stiffness damping parameters, how they vary with respect to strain is also very important to know. It is not that there is a classical or one type of testing solution which majorly in our India or even abroad we use the SPT. SPT is very commonly used, but whether SPT can give us the dynamic properties or not, we need to ask ourselves. If it is not, if it doesn't capture the modulus reduction with strain and the damping variation, then probably we need to do much more to determine the proper dynamic design parameters, and that is essential for any important or major projects. So I have divided the journey or work which we have done at IIT Bombay, the research to practice on these 9 subsections or 9 subtopics, starting from retaining wall and ending with slope stability studies. The first section, the seismic analysis and design of retaining wall, which we started at IIT Bombay soon after my joining over there in 2003, we know that conventional seismic design is always pseudostatic, which Mononobe Okabe long back has given, and in Kramer's book we always refer, that is the first pioneering book in this topic. But there are many questions arises, how to select this horizontal and vertical seismic acceleration, what about the soil amplification, which cannot be considered in the pseudostatic analysis, what is the variation of this seismic acceleration for depth and time, and how the dynamic soil properties are included. So none of these are answered in the conventional pseudostatic approach, and that is why we tried to solve some of this. As I said, my research journey started from IISc Bangalore with my PhD supervisor, Professor Subbarao. I worked on this topic, how to estimate the seismic passive resistance considering the curvilinear failure surface, and we also gave the exit angle solution, the closed form design solutions, which can be seen over here. Also, we have given the closed form design solution along with the design charts, which any engineer can use directly our design charts for obtaining the seismic passive earth pressure coefficient depending on whether positive wall friction angle or negative wall friction angle. So this work done with my PhD supervisor at IISc Bangalore. Now, as I said, the limitations of the pseudostatic approach, the first thing at IIT Bombay when our research journey we started, independent research journey we started, the first research work has been carried out, my first PhD scholar at IIT Bombay, Dr. Sanjay Nimbalkar, who is now Associate Professor at UTS Sydney. I'm thankful to him. He came all the way from Australia. And he developed, which we have published in the Geotechnical journal, one of our leading journal, how to take care all the limitations which I have mentioned for the pseudostatic approach. That is the time duration, the frequency of earthquake, the soil properties, the shear wave velocity, primary wave velocity, all these could be taken into consideration, including the soil amplification in this developed pseudodynamic approach which Nimbalkar developed. From that, we also try to give the closed form design solution both for seismic passive earth pressure as well as seismic active earth pressure, and given these equations, and I will skip these equations quickly. One can refer to those our geotechnic paper, that how this varies with various dynamic soil properties, amplification, and other seismic event component which were not addressed during the pseudostatic method of analysis. Then another beauty of this pseudodynamic method, what was developed, is that you need not to assume the earth pressure distribution, which we typically assume the hydrostatic nature, that is the triangular or linear, which is not the case. It is highly nonlinear, and that gets captured automatically from this pseudodynamic method developed. And as more seismicity, more nonlinearity comes into the place, and how this soil amplification actually increases in case of active earth pressure, the seismic coefficient, that is also important to note, which can be used by the designers. We also validated this closed form analytical solution with the dynamic centrifuge test results available from Cambridge, actually, Professors Steedman and Zeng's, their work. We found that this nonlinearity has been well captured by pseudodynamic method, by the centrifuge test model also, which the conventional pseudostatic or mononomial method cannot consider. Then further extending our work, we thought that why only the soil pressure we need to consider. We need to also consider the wall effect, because it doesn't work isolated way, that soil behaves differently, structure behaves differently. Soil structure interaction is the one which need to be taken into consideration. So further, Nimbalkar carried out his work how to take care of the soil structure interaction for wall soil inertia, and he has developed the beautiful design combined dynamic factor, which is a one-step solution what practicing engineers can use. That once you know what is the stability requirement for the weight of the wall to be provided under static case and the dynamic case, how it should be, that FW factor he has developed, which we has published in various papers. So these are the design factors, how FW can be taken into consideration for the design under earthquake condition, this retaining wall, both in active case as well as in passive case. Next step, my another researchers, Dr. Aninda Pine, who is also present over here, and Dr. Amay Katdore, they developed modified pseudodynamic method. They considered first time the effect of damping factor, which in conventional pseudodynamic was not there. Also the boundary stress equilibrium, that is how all the stress waves or the waves traveling upwards, whether shear wave or primary wave, how this wave equation follows the boundary condition, that also has been captured in this analysis for the retaining wall. The same thing has been further continued with the cantilever retaining wall. Dr. Nandi, Ritik Nandi worked on this topic, that how this design approach can be given to give the closed form design solutions and the design charts. Coming to the second section, which is for the seismic design of the waterfront retaining wall, or we call them also seawall. So for this seawall, typically we considered in our study, this is the work of started with the second PhD scholar, Dr. Syed Ahmed, who is a faculty at University of Manchester in UK. He could not attend today this conference, unfortunately. So we considered how the multi-hazard work. That means when tsunami wave comes, there can be two cases: when tsunami attacks the seawall, that is the passive case, and tsunami wave when it recedes back, that is the active case. So these two cases, when we were trying to publish this research component in various journals, we used to hear a lot of initial rejections from various reviewers mentioning that why you are considering two extreme events together. Then, fortunately or unfortunately, this work has been done during 2006, 7, 8, 9. 2011 earthquake of Tohoku, Japan, we all know, that is an eye-opener. It showed the world clearly that, yes, multi-hazard can happen together. That is what the post-earthquake and the tsunami can come together, which actually make a devastated failures in Japan. So Syed developed several design factors, both using pseudostatic approach, considering both tsunami wave as well as the earthquake, both into the consideration. He has given closed form solution for factor of safety with respect to sliding, as well as factor of safety with respect to overturning. And then for active case also, you know, when the water is going back, there can be two possibilities, that is restrained water case and the free water case, depending on the soil permeability in the backfill soil, and accordingly the design solutions Syed has presented in his thesis. Also, various design charts have been proposed by Syed from his work. Then further, for reinforced soil wall, if those are used as a seawall, that also Syed has mentioned how this multi-hazard, that is earthquake and tsunami, can be taken into consideration for the design, and this easily available for the practicing engineer. The design charts have been given. Later on, my another former PhD scholar, Dr. Rajesh, who is also present over here, extended this work, how this multi-hazard can further be extended using this modified pseudodynamic approach for the seawall, where he has taken both seismic active earth pressure, seismic inertia effect of the wall, non-breaking wave pressure coming from the wave side, hydrostatic pressure and hydrodynamic pressure all into consideration, and he also has developed the design solutions for factor of safety of the wall, so which can be used for the design of such wall. Coming to the third section, that is on seismic design of reinforced soil wall. In this, actually, again, the first work goes credit to Sanjay Nimbalkar. Sanjay tried to develop how the reinforced soil wall we can design under earthquake condition, both considering internal stability as well as external stability, and he has given the design solutions, how much reinforcement force is required to provide, and also how much length of the reinforcement required for the internal stability, also to satisfy the sliding and overturning external stability. So among these three lengths, whichever is maximum, that needs to be provided for design of a reinforced soil wall under dynamic condition. That what Dr. Nimbalkar in his thesis has mentioned. Further, as I mentioned, Dr. Pine has used the modified pseudodynamic approach. Dr. Pine, in his thesis, considered how this reinforced soil wall, both for internal stability as well as external stability, can be designed, considering both S and P wave, ground equilibrium conditions, and all other like damping ratio, viscosities, Lami's constant, everything into consideration in the design approach. Coming to the next section, that is seismic analysis of shallow foundations and anchors. On shallow foundations, this is our starting work. Again, going back to IISc with my supervisor, Professor Subbarao, we developed the pseudostatic design solutions, how a shallow footing both embedded in the horizontal ground as well as in the sloping ground mostly in the hill station or hilly area, we use such kind of shallow foundations, how those can be made stable under pseudostatic earthquake condition. And we have given the design solutions to that. Further extending that work, our another former PhD scholar who is present here over here, Dr. Kshitija. Kshitija worked on this aerodynamic approach using the Taguchi method, and she developed the seismic bearing capacity factors for shallow foundations from her work. Coming to the uplift capacity of anchors, uplift capacity, our another former PhD scholar, Dr. Sunil Rangari, he developed using the Coter's equation and the application of the pseudodynamic approach, how this uplift capacity of ground anchors can be obtained. He has given design solutions as well as the design charts, which are easy for the practicing engineers to use. Then Dr. Pine extended his work for applied to the ground anchors as well for modified pseudodynamic approach for these ground anchors, capacity, how to estimate. Then our another former PhD scholar, Dr. Kedar Birid, who came from industry with a lot of industry experience, he worked on this performance-based design for the ring foundation. So how these ring foundations perform under combined load of this VHM, what we call vertical, horizontal, and moment load, and he has developed design solutions for that, which we have published earlier. Now coming to these are all the basic research. Now we started applying this basic research to the actual field problem when many projects came to IIT Bombay to our lab. So this is the project I'm highlighting, the largest petroleum and oil terminal of India, which is for two countries, our Prime Minister and that time Nepal Prime Minister, they had signed MOU. This project was done at Motihari in Bihar. And this is a highly seismic zone, as you know. This is close to Nepal border, just 50 kilometers away from this site, the Nepal border. And for this project, my another former PhD scholar, Dr. Milind Patil, who is present over here, and Dr. Pradna, they all were involved for this project. And we have established what can be the ground improvement scheme to mitigate liquefaction, because that region being highly seismic and also it is an alluvial soil, so and groundwater level close to ground, so that's why it is prone for liquefaction for such earthquake condition. So how to mitigate that, and that too very deep in the strata? People say that 15 meters beyond that liquefaction will not happen. That is no longer a valid reason. We all have technical proof that it can happen even beyond that. So combinations of ground improvement of vibrocompaction and vibrostone column has been proposed, and Keller performed this work. IOCL initially approached me, so I was both on the owner side initially for the preliminary investigation and the review of the project. Later on, Keller also hired me for their design solutions and all these things to check. So there are several options. The second options were taken for the mitigation of liquefaction. We have actually experienced and seen several field tests. Field tests, as I said, only SPT may not be the giving complete solution. So this is a classical example of an important national project where not only SPT, CPT, and DMT has been included. And I can say here that after the successful application of DMT in this project, we also have included the DMT first time in our Indian standard code IS 1892, which is for geotechnical investigation. So this, Dr. Pradna Singhal, in her thesis, it is there, and we always say women empowerment in geotechnical engineering. She being a lady PhD scholar in the site, she did all the work along with the Keller team in Motihari. So you see how this liquefaction assessment without improvement and with improvement. Without improvement, the entire strata is going to get liquefied. You see factor of safety is much lower than 1 in many cases. And after improvement, you see the result there. Throughout the depth, they have to show that was the requirement of the contract for or the tender, that the agency has to prove that with the improved soil data, it should actually give the factor of safety more than 1. Then when for this petroleum oil terminal, why I said this is largest here, not only the vertical tank has been used, but also MSV, that is mounted storage vessels have been used. We found that initially without improvement, huge amount of settlement is causing. This is MSVs also have been implemented. Vertical tanks have also been implemented for this site. And you see the amount of deformation in millimeter, it's huge. It's non-acceptable without improvement. So then For this, we have, as I mentioned, we did several site visits with KELAR and IOCL. This is the settlement monitoring. Later on, KELAR has to prove, as per their requirement again in the tender, that how much is the observed and differential settlement for the all 17 different types of tanks which have been implemented at the site, and they should perform well. You see, under 200 kPa loading intensity, the settlement came 50 mm with the hydro test, which is less than the 100 mm, which is the permissible limit, and various tank diameters and their rotational displacement also was placed into the required serviceability criteria. So this is the picture which KELAR shared after completion of the project with us at Motihari in Bihar. Extending this, we have done probably for IOCL several other projects throughout the country. This is another project we were involved in Vallur near Chennai for the oil terminal. There also, of course, the soil type is completely different than what we got in Motihari. Here it is completely marine clay, as you know. So here also the ground improvement has been done, and my two former research scholars, Dr. Tanmay Das and Dr. Meghna Sharma, both are present over here. They worked on this project, and we successfully completed this project as well for TC along with KELAR and Bauer both. Coming to the next section, seismic hazard and risk analysis, on which another group of students, they work. We all know about seismic hazard analysis. To this August gathering, I need not to explain that there are two methods of DSHA and PSHA, and these are the 4 steps for each DSHA and PSHA what has been adopted. The first work in our lab on seismic hazard analysis has been done by Dr. Jayakumar Shukla, who is also present over here, for the Gujarat state. Entire Gujarat state, for 25 cities, he has mapped the DSHA and PSHA. And remember, as per the seismic code, this is the only state in India which has probably all the seismic zone, that is zone 2, 3, 4, 5. So that's why it is interesting. If you solve the problem of the Gujarat state, probably you solve for all the zones of the country. And he developed, Dr. Jayakumar Shukla, in his work, all this map for 25 major cities of Gujarat, Ahmedabad city, and he divided into the 3 major regions, Kutch, Saurashtra, and mainland Gujarat. And we found that many of these spectral acceleration, which are coming from our site-specific studies, are actually much higher than the what IS code recommend. That's why. So that's why, as I think Professor Sitaram has mentioned, IS 1893 latest version just came just few weeks back, which proposed the very higher values of PGA. So now our studies, which has been done almost like 10, 15 years back, now I can see that those values are getting translated into the code. I'm happy to see that. So probabilistic seismic hazard of Gujarat, you see, Dr. Jayakumar Shukla again developed for all these things, and he has also developed for 4 important ports of Gujarat, that is the Kandla, Mundra, Dahej, and Hazira port, how these seismic accelerations and spectral accelerations actually comes for the site-specific analysis. Next study in our lab was done for the seismic hazard analysis for the state of Goa. And this work has been done by my another former PhD research scholar, Dr. Nisha Naik, who is also present over here. So Dr. Nisha has carried out for entire state of Goa how this seismic hazard map can be developed. And this is the DSHA map she has developed in her PhD work. And for different cities like Mapusa, Panjim, Ponda, etc., she has developed how this DSHA map will be helpful for design. As well as PSHA map also has been proposed. And here also we found the many region, actually, if we design using our IS code that time, would not have give us the safe design. Now in the revision again, we found that these higher values have been recommended at various places. Next study in our lab was done by Dr. Sarika Desai on his seismic hazard analysis of Mumbai city. And Mumbai city, for Mumbai, Thane, Navi Mumbai region, she has studied both DSHA as well as PSHA. And also, my another former research scholar at IIT Bombay, Dr. Sumed Maske, he has developed a nice risk map for the liquefaction studies in Mumbai. This risk map, as I said, this is not the hazard only. We have to take care of the vulnerability and exposure also. And not only that, through his analysis, he has given for, actually this was well appreciated in the media that time, that this can give the least path to reach to important facilities like hospital, when there is a disaster happen, how to rescue people, and what is the path to be followed. So that also he has formulated in his PhD research work of Dr. Sumed Maske. Later on, extending his work, my another PhD scholar, Dr. Reshma Raskar Phule, she has developed for the cyclic mobility hazard map as well as liquefaction hazard map. As you know, the liquefaction term we use typically for the sandy soil, cohesionless soil, whereas cyclic mobility is the word we use for the clay soil or the soil with fines. So that is what soils with fine, those also have been taken care of by this liquefaction hazard map. Further extending this work for Kolkata city, seismic hazard map has been developed by Dr. Kaustubh Chatterjee, who is also present over here, and he developed the VS-SPT correlations for different types of soil for Kolkata. Now, these are the, again, academic research, and we wanted to apply it in the real field. And that opportunity came when the seismic hazard analysis of nuclear power plant, the new nuclear power plant of GHAVP in Haryana came to us at IIT Bombay. So this work has been done by another former PhD scholar, Dr. V. Dilli Rao. So he has developed for that site, nuclear power plant site, how the distribution of earthquake, what should be the unsmooth and smooth GM, from where the safe shutdown earthquake and OB, that is operation basis earthquake, can be obtained. And for the site-specific shear wave velocity study, SPT and relations also he has formulated for the site. Latest, at present, advancement in the seismic hazard analysis at our lab, one of the present research scholar, Mr. Arindam Das, who is also present over here, he's working on the recently, you may be knowing, the one paper from one of our former postdoctoral researcher, Dr. Ranjit Das, mentioned that MW is not the proper scale for earthquake, though worldwide it is used. So how this value saturates at higher earthquake level and doesn't convey the correct earthquake value, he has developed a new scale of MWG, which is published in BSSA, a well-reputed earthquake engineering journal. And using that for the northern part of India, Himalayan region, Mr. Arindam Das, in his present PhD work, is developing the new GMP. This is the, because GMP always we lack in India. We use the GMP from all over world, but our own GMPs are very limited. So that way he has developed a new GMP. Coming to the next section, seismic analysis of pile foundations and caissons. So you see the first work in our lab was done by one of our former PhD scholar, Dr. V.S. Fanikant, who is head of civil engineering at BARC, Mumbai. So he analyzed how single pile passing through different layers of non-liquefied and liquefied layers, they behave under earthquake condition, considering both kinematic interaction and inertial interaction. Because mostly in the structural design, or when a structural engineer design the pile foundation under earthquake condition, they only consider the inertial component. They miss out the component of the kinematic portion, which probably a geotechnical engineer only can consider this thing. So he has shown how the bending moment of a single pile can exorbitantly increase if it is not taken care of properly in the work. Later on, the P delta effect on the pile also has been analyzed by Dr. Kaustubh Chatterjee's PhD research work. He has done it for FLAC 3D analysis, how a single pile behaves, and how it compares with the JRA recommended formula, how our results compares, and it shows that 1% higher peak bending moment and 23% higher pile tip displacement compared to the JRA method, using our latest method considering the non-linearity due to vertical load and the lateral load effect, and combinations of vertical and lateral load together. Further, his work, Dr. Kaustubh Chatterjee work for group pile also, it has been applied for 2x2 pile group in liquefiable soil. He has carried out in the numerical analysis, whereas the lab testing part has been done by my another former research scholar, Dr. M.K. Pradhan, who is actually from HBNI, BARC. So he has carried out the check table test for 2x2 pile group in liquefiable soil. Now, on the Cation foundation, on liquefaction, as you know, the well foundation or Cation mostly we use below the bridge. This work has been done by one of our former PhD research scholar, Dr. Shibayan Biswas, who is now a faculty at NIT Jalandhar, just recently joined here. So he worked on this topic at our lab for his PhD, how this Cation foundation under earthquake condition need to be designed, considering the liquefaction effect. And we got immediate a chance, a big project came from BRPNNL, that is Bihar Rajya Nigam Limited, for this Patna bridge on River Ganga, how to apply this design concept for the practical project, and that has been used. Then another practical project we have handled at our lab, dynamic soil structure interaction analysis and pile group design for oil tank for a project in Iraq. This project came from BP, British Petroleum, approached us. Then we have designed this. This is also seismically active region, how this region pile need to be designed. This through Dr. Jayakumar Shukla and Dr. Ashutosh Kumar, we all did this project for the Iraq. Then one of our former PhD research scholar, Dr. Sujata Manoj, she is also present over here. She is from Australia. So when she did PhD, she was actually in Dubai working with Fugro that time. She has developed beautiful solutions for the value engineering, what is called the Barrett Foundation. Because Barretts are used for several tall towers in this Middle East at UAE region. So he, along with Dr. Marwan, actually, we developed this FS and UCS relationship for weak carbonate rock, and how this Barrett can optimize the length of the piles and how it can be designed for under seismic condition also she has completed. Coming to our another major project which we have were fortunate to handle at IIT Bombay is the Atal Setu Foundation for Package 1. L&T approached us long back in 2018 for this project. As you might have seen that last year on 12th of January, our Honorable Prime Minister opened this Atal Setu. This is the longest sea bridge of India. That is 21.8 kilometer long, which is called Mumbai Trans-Harbour Link, that we have worked for the foundation and the seismic design component. So this is the location. It connects now Mumbai with Navi Mumbai with the shortest route, just 20 minutes travel, which was earlier 2 hours of travel. And this is a total length, as I said, 21.8 kilometer and 100 plus years of design period. And this is what I have mentioned. This is one of the support system with 2 piers, then pile cap, and below each pile cap there are 2 by 2 piles that has been used. And the critical section was 180-meter long span. Such a huge long span for this longest bridge has been used because, you know, Mumbai port is such an important port of the country, so many big ships have to come. So this is the geotechnical profile of the site. You see, initially there will be the standing water. Below the standing water, there are very soft silty clay, and followed by then the basaltic rock starts coming typically from 30-35 meter onwards. So that way, Mumbai region is having this good founding strata below. So we have carried out the detailed seismic site response analysis for the site, dynamic soil structure interaction for the foundation for the seismic zone 3 of Mumbai, and also one-dimensional equivalent linear analysis. Amplification has been taken into consideration, damping has been taken into consideration, modulus degradation has been taken into consideration. For 4 different types of earthquake accelerations, this has been designed for horizontal and for vertical, so that all the different possibilities are captured. These input motions were given by NGRI Hyderabad, and we have to design with this the foundation component. You see, this is the amount of amplification possible for the site, which we have carried out. As high as 2.18 of amplification is possible up to the depth of that 10 meter, and above that there is a standing water, and we have to design with that high amplification. You see, this is a project where large diameter piles started using in India after that coastal road project, and there are many other projects actually where it has been used. So this project used the pile diameter as large as 2.2 meter, and with so more than a human height actually, and pile length of 36.5 meter, and we carried out all the detailed analysis of the seismic design, how the amplification under each earthquake motion it happens. For this, we have also given the pile load, axial load, bending moment, everything for the site over there. We also have published this paper covering this Atal Setu Foundation, how this has been designed in our Indian Geotechnical Journal. And this is from our field visit where L&T invited us after executing this project at our IIT Bombay. They invited us during the execution of the piles and piers. We visited the site. Dr. Milind Patil was present along with Dr. Anirudh Bhadri and many others present over there that time at the lab. So this is another project we have handled, Indore Metro Foundation, so where the pile foundation has been used, and this is the elevated metro where Dr. Chaudhary Choudhury, who is present over here, and Dr. Dilli Rao, they worked on this project, and when the foundation were not working, all the pile load tests failed. Then they approached us at IIT Bombay how to safeguard this Indore Metro Foundation, because this is the first metro coming in Indore, and for that we could give them the solutions, which also media has well covered how our IIT Bombay's participation was there for Indore Metro Foundation project. Coming to this pile foundation, now the high-rise building, high-rise, as you see, where India stands. Its present global rank, we are 12th in the world, but very soon we will be in top 10 because many high-rises are coming up in India, mainly in Mumbai. So currently being our high-rise committee, one of the high-rise committee member, we know how many projects we are handling every month. There are several failures we also see in the newspapers. These are various newspapers, mainly from Mumbai I have taken because Mumbai being a cluster of all the high-rises in India. So there you see many foundation failure, mostly we see during the monsoon time. There are reasons for that because of the wrong design, nearby construction, non-taking the interference effect, and all those things are major reason. So there is a code IS 16700, which is a tall building code, 2023 version, always suggests that it has to be reviewed if any building height exceeds 250 meters by the expert review panel. And Maharashtra government first came up with this ERP panel. We are listed over there. You can see the name. Recently, last year, Haryana state also came. I request all other policymakers present over here make it for all India. Other states also should come up with such expert panel list. So how this soil structure interaction analysis for this high-rise foundation, considering the interference effect for all the surrounding buildings need to be taken care of, that we have now made it compulsory. Our Dr. Tanmay Das and Dr. Rishabh Vaishya and Mr. Rakesh, they worked on this topic. And from our site investigation and analysis for the high-rise project, we have come up with the details how the inclusion of surrounding building affect your foundation design. If you don't include it, probably you are missing some very important aspect. These are some of the poor examples. Before, just after joining the high-rise committee, I found poor testing, poor construction, poor shore pile. You see the shore pile, concrete doesn't reach, and in the core box, the rocks are actually overfilling. So these all shows how bad sometimes our geotechnical engineering can be if we don't put proper important consideration for this. These are the few good practices which we all know probably we need to follow all these good practices for our design. This is our present high-rise committee of Maharashtra government with the Municipal Commissioner of Mumbai. And this is a recent development. Last year, finally Maharashtra government have recognized independent geotechnical engineer, because so-called, you know, all over India, structural engineers sign on behalf of geotechnical engineer for foundation also. Worldwide also, many places this is the case. But why we structural engineers should take all the responsibility and creditability when geotechnical engineers are involved? So in Maharashtra, at least we could implement this after several deliberations last year. This official circular came on 11th December 2024. Now, geotechnical engineer has to sign all the geotechnical design, and also they are independent signatories and empanel empanelment of geotechnical engineers, we just approved in our last meeting, happened on 6th of December, just last week actually. Very soon the official order also will come. So this Maharashtra government, what has been done, I request again all the policymakers present over here, please do it for the entire country, for other state as well, so that our geotechnical engineers' importance, credibility, everything is recognized and well documented. Coming to next, seismic analysis of combined pile raft foundation, or CPRF. This overview, we all know that pile raft, we generally consider two types, pile enhanced raft or raft enhanced pile. So how this work actually started academically long back in late 70s and early 80s in UK and Germany. Then this is the future of the glory of foundation engineering. You know, 1 kilometer tall, this tower is under construction now in Saudi Arabia in Jeddah. Last 2 years, I happened to attend the Jeddah conference, thanks to Mr. Hamza, present over here. They organized the conference. My present scholar from Bahrain, he's also present over here, one of the sponsor of this event. So this pile raft has been used for this Jeddah conference, and Professor Katzenberg, one of the biggest collaborator from Germany, he was involved in that. So this is the international design manual which we brought out in 2013 ISSMG conference in Paris from TC212. This is the first international design guideline on CPRF, how this pile and raft together need to be designed, how the alpha CPRF to be taken into consideration, what are the 4 different types of soil structure interaction need to be considered for such complex design of the foundation. And these are the textbook and various edited book on which pile raft foundation we have published, and one can see the details of the fundamentals of our pile raft foundations in this textbook, which is available, CRC Press. I'm thankful to our Bureau of Indian Standard. They actually given me the responsibility way back in 2019 by making a convener of this committee under CED 43 to bring out this new code of practice in India, that is on CPRF, which came out this year in March, IS 19117. This is a new code altogether for India, first time. What are the design and construction considerations for this combined pile raft foundation? Actually, the demand came mainly from the industry, thanks to all our industry partners, because they want to implement it without the IS code. It is difficult to implement, so we are thankful to BIS that this code is now in place. On CPRF in our lab, the first research work started by Dr. Ashutosh Kumar. So he worked to give the closed-form, again, design solutions for the bearing capacity of the CPRF, that is with pile, without pile, how this can be changed. And these are the proposed equation for the interaction factor. These interaction factors are very important. As I said, it is a complex soil structure interaction problem. So alpha CPRA, alpha PR, how it changes. That is pile to raft reaction is more important over here. And that has been proposed by Dr. Kumar's PhD thesis work. Another important aspect, one of our former master scholar, along with Dr. Ashutosh Kumar, Dr. Jashod Roy, also worked in our lab, how the inclusion or exclusion of superstructure on the CPRF foundation immensely influence in the design. Because most of the time we geotechnical engineers design the foundation without considering the overall superstructure. We just take the vertical load, horizontal load moment, whereas structural engineers, they do an excellent analysis of the superstructure, but they consider only soil spring for the design of the foundation. Neither are correct, because it is a total altogether combined structure, which is superstructure and substructure together. And this study has shown clearly, if you see, look at the result, that considering superstructure and neglecting superstructure can change your natural frequency immensely, and that is where your resonant condition, dynamic design, everything gets influenced, and that need to be taken care of, including the amplification effect. If you are neglecting superstructure, probably that is not the correct way of design. Also, the pile raft under dynamic loading, considering the Pasternak theory. So our another former PhD scholar, Dr. Aniruddha Bhaduri, he extensively worked on this, how to develop the closed-form solution for this pile raft under dynamic load. Then we have implemented it for the nuclear power plant, nuclear building foundation for CPRF. Is another PhD scholar, Dr. Girish Patel, who is Deputy Chief Engineer at NPCIL now. He worked on this topic for the real-time project of the nuclear power plant foundation and developed this design solutions for this. We got an opportunity for our, again, academic work to translate it to the actual field work of the India's nuclear power plant of GHVP Haryana, which is a special structure and location. I will come to that very soon because of this region. This is probably the first NPP which is fully on soft alluvial soil, because all other NPP of India are on hard rock. So that's why the challenge was with the foundation, not with the superstructure. And this GHVP Haryana, this is a typical nuclear island, what we call all the reactor building, control building, reactor auxiliary building. We have to design the foundation. That is what the work has been given to IIT Bombay. And independent analysis we have carried out. This is the static analysis, as I just mentioned. We cannot work in isolation. We have to do the superstructure, substructure together. So this is an example of whatever complex model you have, but you should model both structure and foundation together. So this is our first iteration model. Because of the classified nature of the project, I am not showing the final result. I will just quickly show you that the raft thickness as high as 7.7 meter at the central location because of the various equipments to be transferred in the nuclear power building. And the pile length of 36 meter with 1.2 meter dia pile has been used. This was too many in numbers, that is 576 pile in the first iteration. Then what is the solution? And settlement also was pretty high on alpha CPR. There is the load sharing with the pile, and the raft was about 80% pile was sharing, which is also not an optimized design process. Then in the second iteration, what has been done? We reduce the number of pile. Any layman will be shocked that how we can reduce for such an important structure the number of piles. Because of the ground improvement has been taken care of. Ground improvement has been done by IIT Delhi was involved, and IISc Bangalore was involved in that project. So that component with the ground improvement layer, we could save huge number of piles, and as you can see, we drop it down to much lower number of piles in this region because of the GI layer has been introduced. And settlement also has been captured. You see the total settlement and the differential settlement, which is most important part for the CPRF, just reduce it to only 10 millimeter for such a huge size of the raft. And the alpha CPRF, which is the most beneficial optimized foundation solution, as you can see, 60%. So see, if 60% load has been shared by pile and 40% has been shared by the raft, which is executed. This is the seismic design analysis which has been done by our another former postdoctoral fellow, Dr. Deeptesh Chanda. He is also here. So this also he has carried out how this dynamic deconvolution and convolution theory can be applied and seismic design can be done for this CPRF. This is from the site visit. NPCIL officials took me to the site after our design when the piles were casted, then raft was about to cast. You can see the picture at the real site. It's such a massive structure you see compared to human height. These are so large because 7.7 meter thick of the raft. Coming to seismic analysis of pipeline and tunnels. So here you see the many pipeline failure. We keep hearing about the seismic cases, underground embedded pipeline. So for this, our former PhD scholar, Dr. Deepankar Choudhury, who is present over here, he developed this closed form solutions, again, how this pipe bending can be captured and seismic forces into consideration for the design of pipes under seismic condition. Earlier, before Dr. Deepankar Choudhury, another former PhD scholar, Dr. Shubhrajit Maitra, in our lab, he also designed the pipes under smooth and rough condition, how this time variation and uplift velocity changes he has actually obtained considering this SSI. Chaudhary also continued his work on soil pipeline interaction under transverse ground condition and surface-induced deformations analysis for the pipeline. And Our another former PhD research scholar, Dr. Milind Patil, who is present over here, he worked on various shallow tunnels actually. He actually analyzed the seismic design aspect of various shallow tunnels, and he has proposed various design solutions, which you can see over here. Not only that academic exercise, we also have executed several practical tunnel problem, mostly in the Jammu-Udhampur highway, the project which Afghans had given us, we have carried out. Dr. Milind and Dr. Choudhury, they all were involved in that tunnel project work, which we have carried out at our lab. Currently, our present research scholar, Mr. Rishabh Vaishya, he is carrying out seismic behavior of the cross tunnels, because many places, because of urbanization, we have the many cross tunnel. How the behavior of the cross tunnel under seismic condition need to be taken care of, that's what he is actually analyzing presently. Coming to the last section, that is dynamic slope stability analysis, and here we all know about several landslide failure, which is a national news or even sometimes international. This is the Kerala news, where the Kerala government constituted a committee way back in 2017-18 during that landslide. And I was fortunate to be a part of that and went to the site for more than 10 days. We were visiting various sites, and massive failure of several large landslide affected area in the Kerala region. So the fault map and the time domain analysis, this has been done during the PhD research work of Dr. Tanmay Das, who is present over here. So Tanmay has presented how this failure can be captured also from our analysis and numerical modeling, which actually happened in actual site over there. He also started implementing in our lab as the present era of AI/ML, where he is also applying how AI/ML can help in our civil engineering, mainly in the earthquake research engineering, this aspect for the design component for the seismic part, and that also has been included in his thesis work for this slope stability analysis. This is a case study he has carried out for the theoretical values to compare with the actual landslide, what has happened earlier. One of our former master scholar, Dr. Ritika Sangroya, she worked if slopes are having pipeline, and in that pipeline, if there is a blast induced, how this affect the slope and the pipeline and tunnel. So that also through the peak particle velocity, and this thing, Ritika actually worked extensively on this topic. Our another former PhD scholar, Dr. Purnanand Savaikar, who is present over here, he extensively studied the municipal solid waste landfill design, essentially the characterization, dynamic properties of the MSW landfill, and then the stability of those MSW landfill under earthquake condition using the pseudodynamic approach, how this critical yield acceleration can be computed, that Dr. Purnanand Savaikar extensively worked on this topic. So with this, another work, last work in this section I'm referring, this is also a case study we have handled, that is seismic stability of tailing dam. This is a actual, in India, you know, one repository is there in the eastern part of India, in Jadugoda actually, where the non-radioactive nuclear waste can be dumped, and the BRC has given us this project long back, how this tailing dam stability under earthquake condition can be designed. That's what we have executed at IIT Bombay. This was in two stages, that is first stage of the dam and the second stage of the dam, that we have designed. One of our former master student, Dr. Deepankar Choudhury and Dr. Sanjay Nimbalkar, both worked on this tailing dam project of BRC, and that has been implemented at the site also with our design. Concluding remarks, this is just, we are trying to showcase summarize our last 25 years of journey in geotechnical earthquake engineering, post-Kramer era, we say, because that is a conventional textbook. There are several researchers worldwide, including our several researchers, as I have mentioned in the starting. They have done this, a small component we have tried to contribute in this large domain of importance in the geotechnical earthquake engineering. And starting with the pioneering work, the pseudodynamic method, then we went to the modified pseudodynamic method, how the multi-hazard problem and risk problem for earthquake, tsunami, landslide can be tackled through both closed form solution, numerical method, lab testing, field experiments, and practical project execution. That is the so far journey. And also thanks to BIS, as I said, because without the codal practice, we cannot implement it in practice. So the CPRF and many other components we could include in our several national as well as international design code, and hope to build for society both sustainable, safe geostructures against this all multi-hazard. So thanks to all my industry partners, I could only show few of them. The major one who has funded majorly at our Geotechnical Earthquake Engineering Lab of IIT Bombay. We are fortunate and blessed to interact with them every now and then for several projects handling at our laboratory, and we learn through their industry experience. That is what I will say, academia and industry interaction, what we are trying to establish and strengthen it further and further. Coming to the acknowledgement part, first, my pranam to all my gurus, that is foundation of my inspiration from the mentors, both from Jadavpur University faculty, Professor Som, Professor Purkayastha, they are no more with us in this world. Professor Shivapriya Mukherjee, I'm fortunate sir is attending over here. My ISC Bangalore, several faculty members, starting with my supervisor, Professor Subbarao, Professor Sridharan, those who have actually shown me and taken my hand with a baby steps to enter into the domain of research. Professor B.R. Srinivasmurthy, Professor T.G. Sitaram, who actually taught us in this foundation engineering, what I'm speaking, the every learning started with sir, Professor G.L. Shivkumar Babu, and many others. My global collaborators, starting with Professor John Bray from UC Berkeley, I learned geotechnical earthquake engineering a lot from him, and Professor Katzenbach, Professor Harry Pulaus, and many co-researchers because of their continuous support, mentoring me, and through have several collaborations. I'm just showing with whom I have papers together. That is what I'm showing. We know our geotechnical field global picture is much more. There are many other names. If I'm by mistake, I'm not able to announce, please pardon me. Indian collaborations, again, as I said, started the independent research from IIT Kanpur, then IIT Bombay, it continues, and ACSIR also. BARC, Department of Atomic Energy is a big support to me because they always give large project. Now also we are in discussion, GHVP now, project 3 and 4, they approached me. We will soon start that. Also the Narora, the second phase, we will start soon. So these are the projects now we are about to start from Department of Atomic Energy. I'm really fortunate to have outstanding scholars in my lab. 47 of the PhD scholars, 36 already graduated from our lab, and 11 are currently working in our lab presently at IIT Bombay. As I said, my postdoctoral fellows, 4 of them are already here, and my various master students with whom I could reach up to the research publication. I have only limited to them. There are many others actually who did masters with us. We not only do our academic work, we have a lot of fun together, many birthday parties, many celebrations, many picnics, and many things we do as a family of what we call GE Lab family together. And this is the living core, my parents, my family over here. And with this, I thank you all. Thanks and namaskar.
Thank you, Deepankar, for that wonderful session. Now, may I call upon Nilanjana Deepankar to come onto the stage, and also Professor T.G. Sitaram and Agnihotri sir, please come down to the stage.
Thank you, sir, for